Hi, Mr. Richards here. Today's lesson is on graphing systems of equations. You'll determine the number of solutions a system of linear equation has, if any, and solve systems of linear equations by graphing. And before we do any of that, we need to take a look at our vocab. Now, our systems of equations can be defined as a set of two or more equations with the same variables for example, y equals 2x plus 4 and y equals negative 2x plus 4. Just one of many examples of systems of equations. Now, consistent. We're going to be looking at the possible number of solutions that a system of equations can have. And if a system of equations is described as being consistent, that means that it has at least one solution. Could have more, but it means it has at least one solution. Basically, the graphs are going to intersect at one point or are the same line. Now, if a system of equations is described as being independent, that is a consistent, so it's consistent and has exactly one solution. And if I want to take a look at what that is, well, if I have a line here, and I have another line here, well, where they intersect here, there's one solution. So that's an independent system of equations. Now, if it's described as being dependent, well, that's again a form of a consistent, but this is where it has infinite number of solutions. It's consistent and dependent. Basically, if I had just one line here, maybe there's two lines, two different equations, but they form the same line. Well, that is an example of a dependent system of equations. Now, inconsistent is when you have no solution. The graphs are parallel. So basically, if I have a line here and a line here, they're never going to touch. They're never going to intersect. There are no solutions. The graphs are parallel, so that is called an inconsistent system of equations. So now we're going to be asked to use the graph to determine whether each system is consistent or inconsistent, and if it's independent or dependent. Well, we have our first equations here, y equals negative x plus 1, and y equals negative x plus 4. Well, y equals negative x plus 1 is the blue line here, and y equals negative x plus 4 is the red line here. Well, those appear to be parallel, and in fact they are. If you look at the slopes are both negative 1, and they have different y-intercepts. One is 1, one is 4, so they have the same slopes but different y-intercepts. They're never ever going to intersect. So that is the definition, once again, of inconsistent. And if it's inconsistent, we don't need to worry about looking at independent or dependent, one solution or infinite solution, since there is no solution. Our second one, y equals x minus 3, and y equals negative x plus 1. Once again, we have x minus 3, y equals x minus 3 here, the green line, and y equals negative x plus 1 is our blue line, and it looks like they have exactly one solution. So we can say, since they have exactly one solution, not only is it consistent where we have a solution, remember consistent can be one solution or infinite solutions, we can also describe this as being independent, since there's exactly one solution right there. For it to be consistent and dependent, it would have to be the same line. Now graph each system and determine the number of solutions that it has. If it has one solution, name it. So we're going to graph these now. We'll start with the first one, y equals 2x plus 3. And 3 is our y-intercept here, so we'll go up to 3. So okay, there's our y-intercept at 3. Our slope is 2, so we're going to rise 2 and go over 1, since it's 2 over 1. We'll rise 2 over 1, rise 2 over 1. Now we can also go from here down 2 and back 1, down 2 and back 1. And I'll go ahead and sketch in this line as best as I can here. Now this next equation is not in slope-intercept form yet, and I would work to get that in slope-intercept form. So if I rewrite 8x minus 4y equals negative 12, if I subtract this 8x from both sides, I'm left with negative 4y equals negative 8x minus 12. And if I divide by negative 4 and divide everything by negative 4, you're left with y equals negative 8 divided by negative 4 is a positive 2x. Negative 12 divided by negative 4 is plus 3. So if I go to graph this, wait a minute, this plus 3 means I have a y-intercept here of 3 again. And I have a slope of 2, so that's going to be the same exact line. So this graph actually has both y equals 2x plus 3 and 8x minus 4y equals negative 12. So I can say that there are infinitely many solutions. And again, this wasn't asked, but this would be an example of a consistent and dependent graph, just to tie it into our previous example. Just notice it's the same line. So it has infinitely many solutions. Now what about this one? Again, neither of these now are in slope-intercept form. So if I rewrite this x minus 2y equals 4, if I subtract x from both sides, left with negative 2y equals negative x plus 4, divide by negative 2 on both sides. You're left with y equals negative y by negative with that x is a positive 1/2 x, and plus 4 divided by negative 2 is a minus 2. So that means my y-intercept is at negative 2, and my slope is rise 1 over 2, rise 1 over 2, rise 1 over 2, and also down 1 back 2, down 1 back 2. You can sketch in the graph here and label this one as the original, which was x minus 2y equals 4. Now for my next graph, x minus 2y equals negative 2. Okay, x minus 2y equals negative 2. Let's go ahead and subtract that x from both sides to get this into slope-intercept form. Negative 2y equals negative x minus 2. Divide by the negative 2. And you're left with y equals negative y by negative is a positive 1/2 x. Negative 2 divided by negative 2 is a positive 1. So when I go to graph this one, my y-intercept is at 1. And my slope is 1/2. So up 1 over 2, up 1 over 2, up 1 over 2. Also down 1, back 2, down 1, back 2. And if I draw on the sketch of this graph, you'll notice that, wait a minute, these graphs are parallel. And this was x minus 2y equals negative 2. We have parallel lines here. So there's not ever going to be an intersection. And since there's not going to be an intersection, there's not a possible solution. So this is no solution. And again, to tie this into the previous example, this would be an example of a inconsistent system of equations. And again, the way you can recognize this, once we get this into slope-intercept form, notice I have the same slope of 1/2 x. They're rising at the same rate, 1 over 2. But our y-intercepts are different. One's negative 2, one's positive 1. So if you're starting at different places on the y-axis and you have the same slopes, there's never going to be a chance to intersect. And that's why there's no possible solution. Now, these are already in slope-intercept form, so if I graph the next one, y equals negative x plus 2, my y-intercept is at a positive 2, and my slope is negative 1 over 1, so down 1 over 1, down 1 over 1, down 1 over 1, or up 1, back, up 1, back. And I'm just going to quickly draw on this sketch right about there. And I'll label that graph y equals negative x plus 2. As for y equals x plus 1, I have a y-intercept of positive 1. And my slope is 1, so up 1 over 1. Up 1 over 1. Or down 1, back 1. And if I draw in this, and that was y equals x plus 1. Hopefully you can see where I do have an intersection right there. And where does that intersection take place? Well, that looks like it is at, for x, 0.5, so a half. And for the y, it looks like it's at 1.5. You'll have that sometimes with the halves. So our answer here is 0.5 and 1.5. We'll write that as an ordered pair. Nina rode 20 miles last week and plans to ride 35 miles per week. Diego rode 50 miles last week and plans to ride 25 miles per week. Predict the week in which Nina and Diego will have ridden the same number of miles. Well, our first step here is to actually write two equations. So let's write Nina's first. Let's say that y is going to equal, well, 35 miles per week. We're going to say that's 35 times x, where x is the number of weeks, plus the 20 that she rode last week. And then for Diego, go Diego, we have y equals 35, or the rate was 25 per week, so 25x plus the 50 that he started. Well, let's graph Nina's. These are counting by tens on this graph, so 10, 20 is the y-intercept. Now, our slope is 35 per week, so if we started at 20, we'd go up to 55 and over to 1, which is right here. Then for week 2, we'll add 35 to that 55, which takes us up to 90. So week 2 would be 90. Week 3 would be 35 times 3, which is 105, plus the 20 is 125. So week 3 is 125, which is right around here. And week 4, 35 times 4 is 140, plus 20 is 160, which is just off our graph, so we'll just kind of write that in there, assume that's there. And we can draw in our graph, our line. Now for Diego. Diego starts at 50. Then for week 1, 25 times 1 is 25 plus 50 is 75. So 1 would be 60, 75, which is right there. For week 2, 25 times 2 is 50 plus 50 is 100. So week 2 would be at 100. Week 3, 25 times 3 is 75. Plus 50 is 125, so 3 would be 125, which is right, hey, there. And just for good measure, 25 times 4 is 100, plus 50 is 150. So right there for week 4, and as we draw in that line, close enough, you will notice that there is an intersection right there. So our answer here, which week was that? Well, week 3. And that's it for this lesson. So just to refresh, we have systems of equations. If a system has at least one solution, it's consistent. It's consistent and independent if there's exactly one solution. It's consistent and dependent if there's an infinite number of solutions. It's inconsistent if there's no solutions. And then we could solve for systems of equations by graphing. Sometimes you'll have exactly one solution like we did here. Sometimes you'll have no solutions if you have parallel lines that have a different y-intercept. And sometimes you'll have an infinite number of solutions if you have the same line. That's it. Good luck.